Hi there, welcome to the 48th episode of the Synth Project, where we are building a synth together. We will spend this episode to complete the construction of the new noise generator module for our synth project. Once done, we will install and test it on the synth rack itself. Let's begin! The case for this module is very simple. The front panel is going to have just two knobs to adjust the level of the noise outputs, as well as two more knobs to select the kind of noise we want to produce. And finally, there are going to be two jack sockets for the noise outputs. 4 holes on the side panel will be used instead to hold in place the PCB with all the circuitry. Here is the case just coming out of the 3D printer. Here instead is the design for the front panel, with all the knobs for the potentiometers and the rotary switches, as well as the position of the jack sockets. This file will be printed on a special water decals paper, which will be put on the front panel of the case, and protected with a few layers of transparent paint. And finally, here is the completed front panel for the noise generator module. While running some tests on the completed circuit, I noticed that I needed to make some slight changes, mostly to better adjust the level of the output noise signals. 5 changes are done on the values of 5 resistors that adjust the corresponding amplification stage. The first change is the value of R5, which changes slightly the gain of the amplifier made by transistor Q1. This is the stage that provides the white noise to all the other elements of the schematic. The second change is on resistor R18 to reduce the gain of the amplifier built around the op-amp U4.1, so to adjust the maximum level of the blue noise. The third change is on the resistors R16 and R17 to adjust the output level of the red noise. The fourth change is on the value of R14, necessary to adjust the level of the pink noise. The fifth and final change is on the output of the violet noise filter. I added an extra capacitor because the filter tends to add a DC component to the output. The series capacitor C52 blocks this DC component before sending the signal to the output amplifiers U7 and U8. Unfortunately, this capacitor was added after the PCB was ready, so I had to cut a track on the PCB itself to be able to attach the capacitor in series with the op-amp U5.2 output. I will show you later how to make such a change to the PCB. It is very easy and should not cause any problem when you do it. Here is the PCB I had made for this synth module. There is a lot of stuff in there, so the PCB is both large and full of components. The first components I soldered to the board were all the IC sockets. Then I installed the connector sockets, and note how I labeled pin 1 of each of these sockets to make sure I did not install them in reverse. After that, I soldered all the decoupling capacitors around the IC sockets. And at this point I decided to assemble the various sections of the circuitry one at a time, so I could test them one by one along the way. I started with the noise generator, which is the white noise. While testing it, I made the first adjustment to the trim pot, so to have a noise signal on the test point with an average voltage of 0 volt. After that, I soldered the components for the pink noise filter. Not all the capacitors necessary to obtain the -3 dB per octave slope of the filter. After testing the generation of the pink noise, I soldered the components for the red noise filter and tested it. Later on, I added the components for the blue noise filter. Then it was the turn for the violet noise filter. This is the one where I had to add the extra capacitor. The one I am indicating is the trace that needs to be cut to add the capacitor. It is the long one departing from the side of the op-amp at the corner and going toward the 8-pin connector. To cut the track, you'll need to use a sharp knife. Use it first to scratch away the paint that covers the copper, so that it is exposed, otherwise we won't be able to solder on it. Then use the same knife to actually cut the track, and be careful not to cut any other close by track. Make sure you form a small gap between the two parts so that they are not electrically connected anymore. To make possible to easily solder the capacitor, it is now necessary to put some solder on the exposed copper. This will also prevent the copper from oxidizing. You can add some liquid rosin to help the process if you like. At this point, you have to shorten the leads of the capacitor, position the two leads on each of the two tracks, hold it in place, and solder it. Once the violet filter was fully assembled and tested, I took care of the green filter, and finally I soldered the components for the two amplifiers. Once the PCB was completed, I started working on the case by first adding a layer of copper tape on the inside to provide a ground plane common to the PCB and the components to be installed on the front panel. Then I installed all the components on the front panel, the two potentiometers, the two rotary switches, and the two jack sockets. Here is how the panel looked like once all that was done and the knobs were attached to the pots and the switches. After that, I added the PCB to the side panel, making sure to orient it such that the power connector lays toward the external edge of the case, to make it easier to connect it to the power railings of the synth rack. And finally, I wired everything together following the schematic. Once you do that, don't forget to do a final tuning of the multi-tone train pot to make sure that the generated white noise has a DC component of exactly 0 volt. If this step is not correctly done, there is a chance that the next filtering stage, or at least some of them, will saturate. In such a case, you won't be able to output the corresponding noise colors. Let's now test the completed module. For that, I have attached the lower output to my oscilloscope, and I powered the module through my new benchtop power supply. Right now, the noise controls are set to maximum level and to white noise. And here is what the oscilloscope shows. If we look at the fast Fourier transform of the noisy signal, we see the expected flat diagram is a function of the frequency, confirming that we are generating a white noise. Note also that the oscilloscope is only showing the FFT in the interval between 0 and 20 kHz, which is even more than what we are interested in, considering that 20 kHz is the maximum frequency that a young person can hear. Let's now go back to the representation in the time domain and test the level adjustment. And you can see that we can effectively go from 0 volt to the maximum and vice versa. Switching now to the pink noise. And here is also the FFT, where we can see that the spectrum is now decreasing at a pace of about -3 dB per octave, in the same range from 0 to 20 kHz. Let's now go to the red noise. And you can see how the slope of the spectrum decreases much faster than before, at a pace of about 6 dB per octave. This instead is the red noise representation in the time domain. Switching now to the blue noise, and here is the spectrum, which definitely goes up at 3 dB per octave, well visible in the range between 0 and 10 kHz, which is the one we care the most. Back to the time domain representation, and let's switch to the violet noise. Here is also its FFT representation. At first glance, it does not seem much different than the blue noise, but looking carefully on the scale, we can see that the spectrum increases at a pace of 6 dB per octave. And finally, here is the green noise in the time domain, and this is its spectrum. In here, notice how it increases from 0 to around 500 Hz with a steep slope, and then it quickly drops afterward, all as expected. Let's now run a quick test on the other input. Here is the white noise, then the pink noise, the red noise, the blue noise, the violet noise, and the green noise, which we don't see because I just forgot to record that part of the test in the lab. Sorry about that. And now this is the module finally installed in the Synth rack on the right side of the dual CPU processor. Let's now run some tests to make sure the generator works also powered by the rack power railings. So let's now hear the noise generator in action. For that, I have connected the lower output to the first channel input of the VCA embedded in the 2130 VCO. The level of the signal for that channel is set to about the middle. And here is the sound of the white noise. This is instead the pink noise. The red noise. The blue noise. The violet noise. And finally the green noise. Let's now go through all of them all at once to have a better grasp of the sound differences. And now let's do the same for the upper output. White noise. Pink noise. Red noise. Blue noise. Violet noise. And green noise. And everything works as expected. Well, we have finally done with this module. In future episodes we will take a closer look at it and see how it can be used not just to generate noise, but also to create a random sequence of control voltages for various usages. Before doing that, though, I would like to make another module that will help putting together all the sounds of the synth, along with other sounds that can be externally generated. This will be something different than a VCA, which could do a similar thing, but it is supposed to be voltage controlled. What I have in mind is instead a stereo mixer, which will allow us to manipulate and put together different sounds that can also be assigned to any spatial position to make the ensemble of electronic instruments connected to it sound like a true orchestra. But we will talk about it in the next episode of the series. In the meantime, I leave you with my usual happy experiments.